Welcome back. So we talked a little bit about what geology is. We talked about some of the names in geology and how we got to where we are. So let's kick it off. Let's talk about Earth. Let's talk about the formation of the Earth. We've got to start somewhere, and that's a good part. That's a good part in geology to start at, I guess, at the beginning. So what is Earth's place in the solar system? Now, the way that Earth formed, the name of that process is called the nebular theory. Remember, theory, highest level of knowing, testable, repeatable, never been proven, false, widely accepted. What the nebular theory states is that the solar system coalesced, came together out of a swirling cloud of interstellar dust and gas called a nebula, and that started, again, about 4.54 billion years ago. Maybe a little bit more. And during this time, around the same time, this is when everything in the solar system formed. The sun, the planets, the asteroids, everything that we have in our solar system formed around the same time. Stars are not in our solar system other than the sun. Different stars formed at different times. So we're just talking about in our solar system, not the whole galaxy, not the whole universe, just our solar system. The sun, the 8 different planets, and a handful of other stuff. So it's in this process that the sun was born via a process called nuclear fusion, which fuses the atomic nuclei of atoms together, releasing a lot of energy, creating that bright light and heat given off by the sun. And it's this theory, remember, highest level of knowing. It's not a guess, not an opinion, scientific theory. This theory explains why also the inner planets are rocky and the outer planets are made of ice and gas. So, what is the nebular theory? So, if you will, imagine just out in space, a cloud of gas and dust just kind of swirling around. The pull of gravity exists with anything that has mass, whether it's something as large as Earth, and the pull of gravity takes this pen and pulls it down to Earth. It's all the way down to just a grain of dust or even a single atom. Anything that has mass has a gravitational attractive force to it. So out in space, if you get even little pieces of stuff, even little molecules, even little flecks of dust, if they have mass, they exist, they're of matter, they have a gravitational pull. If this dust is out in the middle of nowhere with under no influence, little to no influence from any other large bodies, well, that gravitational pull of these two single little things will bring things together. Will bring more things together. And it'll bring more things together. So you have this big cloud of matter, dust and gas and molecules and atoms starting to contract gravitationally. What happens as that material compacts, it also kind of begins to spin. So it squishes and kind of compacts and begins to spin. So it contracts further and further, but spins also faster and faster and faster. So that's when you get into the second thing. It creates this little bulge in the center with this kind of disc, rotating disc around it, spinning faster and faster and faster. As that contraction continues, as the pull of gravity of material continues, temperatures are going up. You're squeezing things closer and closer together to, at some point, the sun turns on. Most of the material is going to be located at the center of this compression of gas and swirling dust. And the material, under the pull of gravity amongst one another, compresses until nuclear fusion happens. So much pull material is fused together, emitting energy, and the sun begins to shine bright. The outer disk begins to cool, and now it starts to cool and form these rings, which eventually these rings lump up together and kind of start this own lump contraction process. Those kind of rings and those lumps in those rings eventually become the planets and everything else. That collection of material of gravity for something to grow larger and larger and larger is called accretion. And within a few tens of millions of years, almost all the debris has accreted into the sun, the planets, and some of the additional material in our solar system, around 4.54 billion years ago. So then the question always is, well, how do we know? How do we know this is occurring? How do we know? We have pictures. Just take a telescope, look in a few different areas, we see it. We see it happening. So we see the nebula. It's the name of a cloud of gas and dust out in space. We see it compressing together. We see it beginning to form disks. We see it segmenting apart. We see it. We see the sun turning, or the star turning on when nuclear fusion begins. We see material surrounding it. We see it. So how do we know? We look at the pictures. It's pretty simple. So again, that formation of material clumping together is called accretion, or planetary accretion. It's an accumulation of sorts. So it's when this outer portion of this spinning nebula cooled into these disks of debris, and a random collision kind of clumped together under the pull of gravity and eventually got larger and larger and larger. This resulted in the planets that were round. Yes, planets are spherical. They are not flat. Let's not even go down that road, right? Gravity pulls in all directions, and when that happens, the only shape that can occur would be a sphere. So the planets are round. They are spherical. They are isolated because they drew in a lot of that gas and dust around it, but so that's why there's large space in between here and Venus, or here and Mars, etc. Because that clump really swept up all that gas and dust that was in its little ring orbit. Any stray rocks that are out there, a lot of them were kind of accreted into planets, but there are still some stray material that's out there, still some rogue material that was never drawn in, accreted by these planets. So Earth is one of 8, yes, 8 planets that orbit around the sun, which also, so in the solar system, there's also over 200 satellites. That's the technical word for moons. If anybody asks, well, how many moons does Jupiter have? The answer is 0, because there's only one moon. Moon is its name. It's a satellite, but it's its name. Just like how many suns are in the whole universe? Well, 1. That's because that's its name. Our star is named the sun. It's a star. Its name is the sun. That's like saying, well, how many Earths are there in the solar system? Well, 1. Why? Because that's our planet. It's its name, Earth. So anyway, I digress. There's over 200 of these satellites, these naturally orbiting bodies around other planets. Moons are what they're sometimes called. But there's also asteroids, comets, meteoroids, dwarf planets, etc. Dwarf planets, what we now know Pluto to be. So that's all the material that's in the solar system, all forming from this process over 4.5 billion years ago. Just curious, I'll never ask this, but can you name the planets in order? I don't know, just curious. Mavem Jasun. So here's a nice little graphic that shows the planets. This isn't location-wise, but this shows you size-wise the size of the planets. Mavem Jasun, Mercury, Venus, Earth, Mars. Mavem Jasun, Jupiter, Saturn, Uranus, Neptune. So these are the 8 main planets. We have the 4 smaller terrestrial rocky planets. We have the 4 larger gaseous Jovian planets. Jovian is named after Jupiter. It's like the king of planets. But then we have also other random stuff. Pluto, which is a Kuiper Belt object. Ceres, and Pluto is also a dwarf planet. Ceres, another dwarf planet out in the asteroid belt. So it's interesting to note, why are these 4 planets small and rocky, but why are these 4 planets big and gassy? What's going on there? How did that happen? And the sun is just so huge comparatively. But getting back to it, well, why are these small and rocky and these large and gassy? What's going on here? Well, it comes back to this spinning nebula. All right. Think about stuff spinning around. Right. If I were to kind of spin around and then throw something, if I had something that was really heavy and I went to go throw it, as I'm spinning around, it's not going to go very far. If I had a bowling ball and I kind of threw it, it might land over here. But if I have a tennis ball, something lighter, and I'm spinning around and I throw it, it's going to go much further. So as this spinning cloud of material is doing its thing, well, why does the heavy stuff seem to stay closer to the sun, while the lighter stuff gets thrown out? Part of that has to deal with that motion. Part of it has to deal with a few other things. So Why are the inner planets rocky? One of those, temperature. High temperatures in the inner solar system, an early inner solar system, reached up to 3,000 degrees Fahrenheit. Really evaporated off and blew out some of that lighter weight material, gaseous elements like hydrogen and helium, leaving behind the heavier stuff that ended up making rocks and the rocky planets. Another is a seismic explosion, maybe a massive concussion wave from when the sun turned on, when that nuclear fusion process occurred, which is the same as what happens in thermonuclear bombs. When that occurred, that could have blown away that lighter material to the further reaches, flung it out to the further reaches, versus the heavier stuff, which kind of just, again, stayed behind. And again, perhaps heavier chunks of rocks were pulled in closer to the sun because of the sun's gravity. The heavier something is, the more attractive force there is. The less massive, the lighter something is, the less pull. So as stuff is being flung around, the gravitational pull from the center of the spinning nebula has less pull on something that's lighter and further away, but has more pull on something that's heavier, pulling that stuff close, leaving the light material out. So there's a number of different reasons why those inner planets are rocky and the outer planets are gaseous. Here are some great songs. When in lecture, when you see these things, they are not just for your amusement. You are required to watch them. Information from here may be asked on any sort of assessment. So in these links, if you pull up the PowerPoint from Canvas, you can click on these links or copy and paste these links, or just watch them and go to them. Make sure you're doing that. So in any case, we'll go ahead and pause here for now. When we come back, we'll talk about what's going on inside the Earth. So we talked about how it formed 4.54 billion years ago via the nebular theory and accretion. Now we'll talk about what's going on the inside. I'll see you back here in just a minute.